Welcome everyone to this month's Spatial ML seminar. And today it's my pleasure to welcome Cheng Zhang. Even though Cheng is still a first-year PhD student, he actually hit the ground running. Was very interesting research that he's going to talk about today. He is a PhD student in the Circuits and Systems group at the Electrical and Electronic Engineering Department at Imperial College London. And he is supervised by professors Aaron Zhao and George Constantinides. And as he's going to tell us today about his research, he likes to do research in efficient machine learning and AI acceleration. And today he's going to talk to us about LLM inference. So Cheng, please take it away.
Thank you, Andrew. Thank you, everyone, for attending the seminar today. Today, I'll introduce the work we published at EMNLP last year. I think it was in June or July last year. The main topic is about quantization, post-training quantization for large language models. Before that, here is a little background about post-training quantization for large language models. As we know, large language model is usually a sequence of transformer layers working in decoding mode. The attention mechanism inside the transformer layer has computational or memory complexity quadratic to sequence length. The matrix multiplication, including linear layer and matmul, contributes to over 90% of computation in large language model. The post-training quantization is a comparison method that approximates a trained neural network in low precision without retraining. As these models are too large and hard to train, post-training quantization is preferred for large language models than quantization aware training. And in the context of GPU inference, post-training quantization is usually classified into weight-only quantization and weight and activation quantization. We'll go back to these two types of quantization at the end of the seminar. Here is a background about the integer quantization on GPU. It's quite similar to fixed point quantization, but as we know, GPU only support integer. The blue square on the left is half precision matrix. Integer quantization approximates this matrix using, sorry, I can use this. Approximate this half precision matrix with this integer matrix and a scale plus a 0 point. So this 0 point is optional. It's usually used to make sure the exact match of zero value. During the inference, the main computation will be the integer matrix multiply. But this one doesn't work well on a large language model because of the quantization error. The common way of integer quantization is they call it per token or per channel integer quantization. This is also called vectorized integer quantization in some other literature. Basically, it's like each row or each column of the integer matrix share a single half precision scale. And the figure at the bottom is an example of a linear layer approximated by this per token per channel integer quantization. In large language models, per token means each row of the activation, and per channel means each column of the weight if we put the activation on the left and weight on the right. During the inference, the main computation is the inner product between two integer vectors. So this is the background. The problem of large language model, I think we started this project in January last year, is that the per tensor or per channel integer quantization fails on larger models. So it may still recover the accuracy on models smaller than 2.7 billion parameters, but for larger models, it just fails. And the baseline back to then cannot reach the precision lower than 8-bit. Here's the problem, and here is our motivation or observation. We do statistical profiling of tensor variance across these model layers, across the decoder layers or transformer layers. So if we look at the figure on the right, the y-axis is the variance of the flattened tensor. Tensor here includes activations and weights. The x-axis is the layer number. We observe that the variance of most activation will increases with the layer number. So the deeper the layer, those activations has a larger dynamic range. And activation consistently requires a larger dynamic range than the weight. So the dash lines at the bottom are the weight, and those on the top are activations, and we use a log scale. We think it might be helpful to take care of that large dynamic range required by the activation. We observe this trend in larger models. The figure on the right is a smaller model and a medium model. We can see this trend of increasing dynamic range is more obvious on larger models. This one is the largest among these three. We also observe this trend in models out of OPT family. So other large language models have similar trend of this large dynamic range required by activations. Then we think the exponent or the scaling part of this format might be helpful to keep or preserve the activation dynamic range. In this work, we basically try out this block-based floating point or mini float on models and conducted a series of experiments to show that to compare which one is best and what's the limitation of the best. The well-known one is the block floating point, which is also called MXInt recently. This one is similar to per token or per channel integer quantization because the inner product between two blocks is mainly about the inner product between two integer vectors plus calculation of the scale. Then this section is about how we evaluate our PTQ masters. In this section, we use uniform precision, which means we quantize the activation and the weights into the same precision. There is no mixed precision in this section. Next is we, besides the software metrics like perplexity or downstream task, we also evaluate the model size or the weight size. We define the memory density as the inverse of average bit width normalized by single precision floating point. So the higher the memory density, the smaller the model. We also use this concept of arithmetic density, which was introduced in BFP paper. It's roughly estimated the compute cost defined as the number of max per circuit area normalized by single precision Mac. Here are some visual results. The software metric shows that BFP or MXInt is the one we introduced in the previous slide, one of the log arithmetic that closest to single precision. So in these two figures, the y-axis on the top is perplexity. A lower perplexity means a better model, and this one is mean accuracy. The higher accuracy means a better model, and x-axis are model sizes. The green curve is the single precision model, and the right one is 6-bit BFP. So we found that BFP is the best among other block-based arithmetics. The limitation of BFP is 6-bit. So 6-bit, 7-bit, or 8-bit BFP is nearly lossless, but if we go beyond that, if we use 5-bit or 4-bit BFP, the quantization will fail. If we match the perplexity or mean accuracy, 6-bit BFP is more hardware efficient than other baselines because they basically are like 8-bit or half precision baselines. The next section is about how can we reach precision lower than 6-bit because the uniform precision, because the lowest uniform precision is 6-bit. This is the last section of that paper. It's about mixed precision search. In the search group, we will try to sample the layers or operations in the large language model and assign it precision using this search algorithm called TPE algorithm. And we estimate the software metrics and the hardware metrics we mentioned in the last slide, use it as feedback to guide the search strategy. The conclusion is that if we use mixed precision search, it really helps to recover the accuracy. The figure on the top, this one, the blue, so the y-axis is the mean accuracy again, and the red curve is single precision. The blue curve is 4-bit uniform precision, which means we quantize all the operations into 4-bit and max int. And the orange one is the mixed precision with average bit width of 4-bit. So we can see the mixed precision search will pull up the accuracy from a poor level to a level close to single precision. And this bar chart is a distribution of precision across layer IDs. We repeat the search a few thousand times, then we found some layers are consistent assigned high precision than others. If I remember correctly, there was a paper called Flight LLM at FPGA this year. They also use mixed precision to recover the accuracy. So until the page to page 6, so until this page, this was the work we started in January and published in June or July last year. What happened after that, or what happened, what the PTQ looks like now? So since the GPU is still the most popular choice for inference or training, most of the work still can be categorized into weight-only quantization and activity-only quantization. For weight-only quantization, most of recent works will keep activation in half precision. If half precision is enough, they don't need single precision. And they use grouped integer quantization to recover, to minimize the quantization error. So grouped integer quantization means here we have an integer weight where each group has several, probably 64 or 128 weight elements. So these 128 integer values share a single half precision scale, and we will have many groups in this integer weight. This is the quantization, and at inference time on GPU, this integer weight will be dequantized or scaled back, casted back to half precision, and do the matrix multiply in half precision. This method can, of course, this will save lots of GPU memory because the 4-bit integer weight. It has speed up on small models or in memory bound case because 4-bit integer will save the memory bandwidth of loading weight from VRAM global memory to shared memory. But this one will actually slow down the inference if the model is large or batch size is large, because in that case, the inference will be compute one. Another setup is weight activation quantization. Oh, sorry, if we go back a bit. So the way they keep, why they keep activation in half precision is because they don't want to touch the activation outliers. They want to keep the activation as it is. then they don't. Then it's not required. It's not necessary to solve this dynamic range. And this group integer quantization, I think it can be regarded as some sort of block floating point in GPU's favor. And next is the weight activation quantization. This one, they use a scale matrix S here to scale down the activation before quantization. And they need to scale up the weight accordingly. So this one will like reduce the magnitude of all activations. They scale up the magnitude of weight matrix. Then they got this, and then they use this per channel or per token quantization to get the quantized activation and quantized weight. So how does this scaling work? This scale is like, if we let multiply the invertible matrix with activation, we can fuse it into the weight, right? And this as can be fused back into the weight of the previous layer. And they only need to make sure S is invertible. And most of the work is mainly discussing how they calculate or how they train this S. At the inference time, weight and activation quantization is just per channel per token integer, which we mentioned before, like it's mainly about the integer in the product. Here is a summary of recent works that can be classified into these two categories. I'm kind of like, I think is the work I published last year kind of predict or line up with how existing work deal with activation layers. They use finer green quantization like this stuff, like this MX int like stuff, and they need to take care of the activation outliers in different ways, mainly in two ways. The most representative work in weight activation quantization is smooth quant. I think it's published by a research group in MIT. And weight only quantization work is called GPTQ, published by ETH, I think. Yeah, I think that's all of my sharing today. Thank you everyone for attending the seminar and questions.